In the spring of 2023, something went wrong on a machine that had never really gone wrong before. For 46 years, it had done its job without complaint, sending home a steady stream of numbers from a place no human had ever visited. Then one day, the numbers stopped making sense. The signal was still arriving. The spacecraft was still alive, but what it was saying had turned into nonsense, a string of ones and zeros that no engineer on the team could read. For 5 months, humanity's most distant machine talked to us in a language nobody could understand. This is the story of what happened during those 5 silent months and what NASA found when they finally got Voyager 1 to speak again. To understand why this moment mattered so much, you have to understand what Voyager 1 actually is, and how strange it is that it was even still running in 2023 at all. It launched on September 5th, 1977 from Cape Canaveral, riding on top of a Titan Centaur rocket. Its job was small and specific. Fly past Jupiter, fly past Saturn, take pictures, gather readings, and then fade into silence somewhere around 1981. Nobody at NASA in 1977 expected this spacecraft to still be sending data back in the next century. They built it to last 5 years. Maybe, but Voyager 1 kept going. It flew past Jupiter in 1979 and gave humanity its first real look at the storms swirling on that planet's surface. It flew past Saturn in 1980 and kept its cameras rolling on the rings. Then, instead of shutting down like it was supposed to, it kept moving outward, using the gravity of each planet like a slingshot, gaining speed with every pass. By the end of the 1980s, it had already become the most distant object any human being had ever built. And it just kept climbing. In 2012, 35 years after launch, Voyager 1 did something no spacecraft had ever done. It crossed the heliopause, the outer edge of the bubble our sun blows around itself. Everything inside that bubble, every planet, every moon, every human life that has ever existed, sits inside the reach of the solar wind. Beyond that edge is a completely different environment, the space between stars. When Voyager 1 crossed that line, it left the solar system behind and became the first human-made object to travel in true interstellar space. And it kept transmitting. That's the part that still amazes scientists today. We have a working instrument sitting out in the space between stars, an environment we had only ever studied from a distance, through telescopes, through math, through theory. Now we had something actually there, sending back real numbers. And those numbers didn't match the theory. For decades, physicists had modeled interstellar space as calm, thin, cold, quiet, a kind of empty hallway between star systems where nothing much happens. Starting in 2017, Voyager 1's plasma wave instrument picked up something nobody predicted, a steady, ongoing hum in the plasma around it. Not a one-time blip, a signal that kept showing up year after year across hundreds of millions of miles of space. Researchers who studied it, publishing their findings in the journal Nature Astronomy, concluded that interstellar space wasn't the smooth void the textbooks described. It had structure, it had motion. It behaved more like weather than like empty hallway air. There was more waiting at that boundary than just the hum. Back when Voyager 1 first crossed the heliopause in 2012, scientists had assumed the crossing would feel gradual, like a river slowly blending into the sea. The solar wind would thin out, the interstellar medium would slowly take over, and somewhere in between the two would blur together. Instead, the instruments recorded something closer to a wall. Particles at that edge were moving at a meaningful fraction of the speed of light, colliding with enough energy to generate temperatures far hotter than anything expected in that kind of thin, empty-seeming space. Some scientists studying the readings started describing the boundary less like a soft edge and more like a barrier of high-energy particles standing between our solar system and everything beyond it. Then came the magnetic surprise. For years, the working theory said the sun's magnetic field and the galaxy's magnetic field should behave like two separate systems, cleanly split at the heliopause, each minding its own business. What Voyager 1 actually measured was different. The field lines on both sides appeared to be linked, interacting with each other, in a process called magnetic reconnection, where lines from two different sources rearrange themselves and release energy. In other words, our solar system isn't magnetically sealed off from the rest of the galaxy the way older models assumed. There's an exchange happening at the edge, a kind of open border nobody had mapped before. That detail matters for reasons that go beyond curiosity. The heliosphere, the bubble the sun creates around our solar system, isn't just a scientific boundary line. It acts as a shield, deflecting a large share of the high-energy cosmic radiation that streams in from distant, long-dead stars, keeping the inner solar system, including Earth, comparatively safe. If the environment pressing against that shield from the outside is more energetic, more turbulent, and more electrically connected to our own system than anyone had modeled, then understanding exactly how well that shield holds up over long stretches of time becomes a more urgent question than it used to be. Nobody is sounding an alarm about it. But the fact that serious researchers now have to ask the question at all says something about how incomplete our picture of home really was. That discovery alone would have been enough to make Voyager 1 one of the most important scientific instruments ever built. But then, in the spring of 2023, it nearly died. The trouble started with the spacecraft's telemetry, the stream of data it sends home describing its own health and its scientific readings. Suddenly, that stream turned to garbage. Not silence, garbage. The spacecraft was clearly still receiving commands and still transmitting something, but whatever it was trying to say came out scrambled, unreadable, useless. For the engineers at NASA's Jet Propulsion Laboratory, this was new territory. They had handled all kinds of problems over the decades, but never one where the patient was talking, just not making sense. They began digging through the wreckage of the signal, trying to find a pattern, a clue, anything that would explain what had broken. Eventually, they traced it to a single component, one memory chip inside the spacecraft's Flight Data Subsystem, the computer responsible for packaging up science and engineering data before sending it home. That chip had degraded after nearly 5 decades of nonstop exposure to the radiation of deep space. It was a tiny piece of 1970s hardware, and it had quietly failed, corrupting a small but critical section of the code responsible for formatting outgoing messages. Under normal circumstances, you fix broken hardware by replacing it. That option didn't exist here. Voyager 1 was more than 15 billion miles away, and no rocket, no robot, no future mission was ever going to reach it in time to swap out a chip. The only tool available to JPL's engineers was radio, and even radio, moving at the speed of light, took over 22 hours just to reach the spacecraft. Another 22 hours for any reply to come back. A single question and answer exchange with Voyager 1 ate up nearly 2 full days. Picture what that actually meant for the team trying to fix it. They would study a fragment of corrupted data, form a theory about the cause, write a set of test commands and send them out. Then they would wait. A full day would pass before they even knew if the command had arrived. Another day before any response came back. They'd study that response, adjust their theory, write new commands, and start the wait all over again. Every step of this process ran the risk that one wrong instruction, sent across 15 billion miles with no way to recall it, could end the mission permanently and irreversibly. There was no room for guessing. Over months of this slow, careful back and forth, the team pieced together a solution. They couldn't repair the damaged chip. It was physically broken, and there was no way to fix broken hardware from Earth. But they realized they could work around it. The code that had been corrupted could be split into smaller pieces and stored elsewhere in the spacecraft's remaining working memory. Each piece would need to be individually rewritten so it could still function correctly from its new location, and then reconnected so that together they still did the same job as before. It was essentially remote surgery, performed through a communication delay of nearly 2 days, on a patient built in the Nixon administration, sitting far beyond the orbit of every planet in our solar system. In the middle of 2024, it worked. Voyager 1 came back online, and this time its data made sense again. Complete, clean, readable science, flowing home across billions of miles just like before. The spacecraft that had gone silent for 5 months, and that many people quietly worried might never speak clearly again, had come back, and almost immediately, it resumed sending more evidence of that strange, persistent hum in interstellar plasma, more proof of a universe outside our solar system that behaves nothing like the old models predicted. That near-death experience in 2023 wasn't the end of Voyager 1's troubles. It was, in a way, a preview of the bigger challenge the mission is facing right now, in 2026. Not a broken chip, but a dwindling power supply that cannot be repaired, only managed. Voyager 1 doesn't run on solar panels. Out where it travels, the sun is far too dim and distant to power anything. Instead, it carries 3 radioisotope thermoelectric generators, devices that turn the heat given off by decaying plutonium-238 into electricity. When Voyager 1 launched in 1977, those generators produced around 470 watts. Today, after nearly 49 years of steady decay, that number has fallen by roughly half. The spacecraft loses about 4 watts of available power every single year, and there's no way to add more. What's left has to be rationed, instrument by instrument, year by year. This year, that rationing forced a hard decision. On February 27, 2026, during a routine maneuver, Voyager 1's power level dropped further and faster than engineers expected, nearly tripping a safety system called undervoltage fault protection, an automatic shutdown mode built to protect the spacecraft, but one that would have required a long, risky recovery process to reverse. To keep that from happening, the team made the call to voluntarily shut down one of the spacecraft's remaining instruments before the crisis could force their hand. On April 17, 2026, engineers at JPL sent the command that switched off the low-energy charged particles experiment, an instrument that had been running almost without a break since 1977, gathering data on charged particles from the sun and from deep in the galaxy. It wasn't broken. It was working perfectly right up until the moment it was turned off. It was shut down purely to buy the rest of the spacecraft more time. Of the 10 scientific instruments Voyager 1 launched with, only 2 now remain active. One that studies plasma waves, and one that measures magnetic fields. Every one of these shutdown decisions is made years in advance, mapped out carefully by a team that knows exactly what it's giving up each time. And every decision is final. There's no switching an instrument back on once its power has been redirected elsewhere. Or at least that used to be true. Right now, the Voyager team is testing something they've nicknamed the Big Bang procedure. Not an explosion, but a complete rewiring of how power flows through the spacecraft. The idea is to swap out a group of older, power-hungry components all at once for more efficient alternatives, freeing up enough electricity to keep the spacecraft systems warm and functioning for longer. It's a risky move on a machine that is pushing 50 years old, with no repair crew and no way to undo a mistake. So the team is testing it first on Voyager 1's twin, Voyager 2, which has slightly more spare power and sits somewhat closer to Earth, making any failure there less catastrophic. Those tests were run in May and June of 2026. If they go well, the same fix could be attempted on Voyager 1 itself, with an earliest possible attempt no sooner than this coming July. And here's the detail that matters most. If it works, there's a real chance that the instrument just switched off in April could be switched back on. Nobody on the team is promising that outcome, but they are trying. Because if the history of this mission has taught them anything, it's that betting against Voyager 1 has never been a smart bet. There's another milestone coming this year that has nothing to do with instruments or power, but everything to do with distance. On November 15th, 2026, Voyager 1 is projected to cross exactly 1 light day from Earth, a distance of roughly 1 billion miles. At that range, a radio signal traveling at the fastest possible speed in the universe takes a full 24 hours just to arrive. Send a command on a Monday, and you won't know if it landed until Tuesday. You won't hear back until Wednesday. No object built by human hands has ever been that far away while still talking to us. And Voyager 1 will cross that line while it is still alive, still transmitting, still adding to a data set nobody else in history has ever collected. It won't stop there. Every hour it moves roughly 38,000 miles farther out. There's nothing in interstellar space to slow it down. No air, no friction, no gravity strong enough to meaningfully pull it off course. The distance will keep growing. The power will keep shrinking. And sometime in the 2030s, most likely, the last usable instrument will finally drop below the minimum power it needs to function, and the very last signal will begin its day-long journey back to Earth. Even then, Voyager 1 won't stop moving. There's nothing out there to slow it down or wear it out. It will simply go on, silent, gliding through the dark at 38,000 miles an hour, carrying something that will long outlast the spacecraft itself, the golden record. Bolted to its frame is a gold-plated copper disc holding greetings recorded in 55 languages, the sound of rain, the sound of ocean waves, the sound of human laughter, and 90 minutes of music drawn from cultures across the planet. It carries diagrams explaining basic science and a map made from the positions of pulsars, meant to show whoever eventually finds it exactly where in this galaxy this record came from. Carl Sagan, who helped put it together, once called it a message in a bottle cast into the cosmic ocean. That description has aged well. Long after the last signal from Voyager 1 has been received and logged, long after the mission is officially closed, and the engineers who worked on it are gone, the record will still be out there, unread, undisturbed, and intact. It will still be traveling when every satellite currently orbiting Earth has burned up or gone dark. It will still be traveling after the cities we live in have changed beyond recognition, after languages have shifted, after entire nations have risen and dissolved. In the truest sense, it may be the most durable object our species has ever made, and it is riding right now on a machine that runs on less power than the small bulb inside a refrigerator. There is still one open question hanging over all of this that nobody has been able to answer yet. That strange, steady hum Voyager 1 has been picking up in interstellar plasma since 2017. Scientists still aren't sure exactly what's causing it. It might be ordinary thermal vibrations in the plasma, something that fits comfortably within existing physics. Or it might be something called quasi-thermal noise, a different mechanism entirely, one that would force a real rewrite of how we model the space between stars. Telling the two apart would need either a lot more data from Voyager 1, which is producing less every year as instruments go dark, or an entirely new mission built specifically to study interstellar space. No such mission currently exists. No such mission is funded. If one were approved and launched today, it wouldn't reach the heliopause for at least 25 years, which means that whatever question Voyager 1 leaves unanswered when it finally falls silent will very likely stay unanswered for a long, long time. The only live window humanity has ever had into interstellar space will close, and it won't reopen for decades. Before that happens, teams of scientists across the world will keep mining every scrap of data the spacecraft manages to send home. because they know they are watching a resource that cannot be replaced or repeated on any timeline that matters to their own careers. Every extra month, Voyager 1 stays awake as another month of a dataset that literally does not exist anywhere else in the historical record of our species. It's worth remembering, too, that none of this was guaranteed. In 1977, nobody signed off on a 49-year mission. Nobody planned for interstellar plasma readings or magnetic reconnection at the edge of the solar system, or a spacecraft still doing useful science while humanity argues, invents, and rebuilds entire industries back on Earth. The mission succeeded far past its design life because a small, dedicated team of engineers kept finding ways to squeeze a few more years out of aging hardware, one careful decision at a time, refusing to declare the mission over just because the original plan said it should be. So here is where that leaves us right now in 2026. The only working scientific instrument our species has ever placed outside our own solar system was built using technology that predates the personal computer. It runs on a trickle of power smaller than a household light bulb draws. It nearly went silent forever in 2023, and engineers brought it back through nothing but patience, 2-day round trips of radio silence, and extraordinary care. It's losing power every single year with no way to refill the tank. And it is still, right now, sending back information that is reshaping how physicists understand the space just beyond our front door. We've built bigger machines since then. More powerful ones, far more expensive ones. None of them have told us what this one has told us, because none of them have been out there long enough or far enough to find out. Voyager 1 didn't succeed because it was advanced. It succeeded because it kept going, decade after decade, long after everyone expected it to stop. Somewhere out past 15 billion miles, a machine the size of a small car is still listening, still speaking, still crossing ground no probe has ever crossed, still running on less power than the bulb over your stove. For a little while longer, it's still ours to hear. The question worth asking is whether we're paying attention while we still can.